A particle, which we think of as a solid thing, really exists in a so-called superposition, a spread out wave of possible locations. And it's in all of those at once. The instant you check on it, it snaps into just one of those possible positions.
It's easy to generate situations where the equations of motion will predict that, say, the wave function, the psi of a certain basketball, is uniformly distributed all over the basketball court. We don't have any idea what a state like that would look like. According to the law of quantum mechanics, that's supposed to be a state in which it fails to make any sense even to ask the question, where is the basketball? That is, according to the law of quantum mechanics, asking the question, where is a basketball whose psi is uniformly distributed over a whole basketball court, is the logical equivalent of asking about, say, the marital status of the number 5. Okay? It's not that you don't know the answer, you don't happen to know whether the number 5 is married or a bachelor. It's that the question somehow is radically inappropriate in the first place. The number 5 doesn't have a marital status, there's nothing there to ask about, and similarly, a basketball whose wave function was uniformly distributed over the entire basketball court would not have a position that could even coherently be asked about. Now, the crux of the measurement problem is precisely that, although the Schrödinger equation predicts under certain circumstances which we basically know how to reproduce in the laboratory, that basketballs should go into states like that, states where there fails to be any intelligible fact, any sensible question even about where they are. And yet, when we go look at the basketball court in situations like that, we invariably see either a basketball over here or a basketball over there or a basketball over there. The fact that we see the basketball in some specific location as opposed to seeing it in some science fiction state that we can't even imagine what it looks like, where there fails to be a question about what its location is, the fact that we always see it in some definite location is an explicit violation of these equations of motion, and it's exactly there that the measurement problem comes up.
You observe, things happen. When you don't, they don't.
Superheroes use superposition, with the world being potential strips of reality, until we choose. Heroes choose what they want, being in many places at once, experiencing many possibilities all at once, and then collapsing on the one. The question is, how far down the rabbit hole do you want to go?
Your own mind is creating multiple possibilities in your subconscious. The superpositions of possibilities are in your subconscious. I mean, you may be consciously aware of them, but they exist, I think, in superposition of multiple possibilities, which after a while will collapse to one or the other.
Project or plan into the future or cast thought ahead of itself.
Nice shot.
But the great-great-granddaddy of wacky quantum weirdness is entanglement. If time reversal symmetry destroys the notion of time, then entanglement crushes our experience of space. Two objects, two electrons created together, are entangled. Send one to the other side of the universe. Now, do something to one, and the other responds instantly. Instantly. So, either information is traveling infinitely fast, or, in reality, they are still connected. They are entangled. And, since everything was entangled at the moment of the Big Bang, that means everything is still touching. Space is just the construct that gives the illusion that there are separate objects. Are we far enough down the rabbit hole yet?
You now can see in numerous labs around the United States objects that are large enough to be seen by the naked eye, and they are in two places simultaneously. And you can actually take a photograph of that. Now, I suppose if you showed a photograph, they'd say, oh, great, here's this nice blob of colored light, and I see there's a bit of it over here, and another bit of it. So you got a picture of two dots. What's the big deal? Superposition is pre-detection. What I was speaking about in the film is post-detection. Now, under normal circumstances, a single object, once it has been detected, is in just one position. However, there are states of matter that have been created now in which objects can be in multiple positions simultaneously, not just two, but actually as many as 3,000 positions. The first of these objects were called Bose-Einstein condensates. And they are single wave functions, meaning they are single particles. But even though they're a single wave function, the wave function has multiple positions. And if you say, well, look right in the chamber. You can see it right there. Oh, I see two things there. You say, no, that's not two things. That's one thing. It's the same thing in two places. Tricky point here is that it's still a single wave function. It's not 3,000 separate wave functions. It's one wave function. So it's one particle. I'm not sure that people's jaw would drop about it, because I don't think people really believe it. And I don't mean that people say, oh, you're lying, or oh, the scientists are confused. I think it is so mysterious that you can't even understand how amazing it is. One particle in 3,000 different locations.
Now, if you were to weigh one of them, would it weigh 1/3,000th?
Well, you can't weigh one of them.
Why?
Because it's one particle. It's one indivisible particle.
But if it's in different locations, can't you put a scale under one?
No, it's inseparable. It's not this is the tricky conceptual part. That it's not 3,000 separate parts.
Even though it looks that way.
Right. You can look at it, and you can't actually see the one with 3,000, but you can look at the simpler ones, the ones that are 2 or 3 or 4, and you can see, as I say, if you go onto the web, you'll see photographs of these. You'll see these little dots floating in space, and these are the different parts of one object. They're not separable. It's not 4 different objects or 6 different objects. It's one wave function. It's one object.
That's a real brain fart, isn't it? Because when you think about it, you just, wait a minute, no, they're like here, 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 so it's obviously 1, 2, 3.
No, you can't, and you can't pull one away from the others. If you try to pull one away from the others, the entire thing will just disappear. And